It is an important lecture as the mathematical tools discussed in this lecture will be used extensively throughout the subject. We can convert a signal from time domain to frequency domain by taking its Laplace transform, and many times we will be required to do the opposite, basically turning a signal from frequency domain to time domain. The inverse unilateral Laplace transform of a function fs is given by 1 upon 2 pi iota integration of fs multiplied by exponential of st from the limits c minus j infinity to c plus j infinity, where c is a real number that lies to the right of all the poles of the Laplace transform function fs. Poles are referred as the roots of the denominator of a Laplace transform function. Everyone should be aware of this expression, but we generally don't use this formula. As we have seen in the previous lecture, we have some basic signals and their Laplace transform. By using them along with the properties which we have discussed and doing little bit of modifications, we are generally able to find inverse Laplace transform via the help of Heaviside residue theorem. If the Laplace transform, which is generally in the form of numerator and denominator, where both are polynomials and the degree of numerator is smaller than the degree of denominator, as well as the denominator can be factored into distinct factors, but there can be different cases of the factorization of the denominator, which we will discuss, like the one which is shown, where all the poles appear only once, which are also referred as simple poles. In this case, we will separate all the distinct factors and will find the different coefficients a1, a2 and so on. These coefficients a1, a2 etc. are known as residues of the Laplace transform function fs. As per the theorem, we can find the residues like a1 by multiplying the Laplace transform fs with a linear factor of which we are supposed to find the residue, and afterwards putting the value of the linear factor to be equal to 0, which will give s plus a1 equal to 0, which will ultimately give s is equal to minus a1. By doing this, we have to find all the residues, and we also know the inverse unilateral Laplace transform of 1 upon s plus an is equal to exponential of minus a n t into unit step signal. After finding the value of different residues and putting in this equation, we can find the signal in time domain. The second case can occur when any pole is repeated. For reference, we have taken s plus a1 is repeated n times. In this case, we will be having n different residues for s plus a1 factor corresponding to its different powers. The later expression we will ignore, as it is simply the previous case where all the factors have been multiplied only once. We can simply solve it similar to the way we have solved in the previous case. Now, to find the residue an, we have to multiply its denominator expression with Laplace transform expression, and afterwards we have to put s plus a1 equal to 0. Residue an minus 1 will be equal to 1 upon 1 factorial into differential of Laplace transform variable fs multiplied by s plus a1 raised to the power n, and afterwards, after differentiating it, we have to put s plus a1 equal to 0. This pattern will continue, and finally the residue a1 will be equal to 1 divided by n minus 1 factorial multiplied by n minus 1 times differentiation of fs multiplied by s plus a1 raised to the power n, and after differentiating it n minus 1 times, putting s plus a1 equal to 0. The unilateral Laplace transform of 1 divided by s plus a1 raised to the power n is equal to time t raised to the power n minus 1 multiplied by exponential of minus a1 multiplied by time t into unit step signal, the whole expression being divided by n minus 1 factorial. By putting the different residues and converting them into subsequent inverse unilateral Laplace transform, we can find the time domain signal of Laplace transform function fs. The third case is when there are complex poles. The Laplace transform function can be represented as sum of as plus v divided by s square plus as plus v, where in the denominator we have assumed s square plus as plus v is having complex poles, and another term is represented which is f1s. This we are assuming it is either the case of repeated poles or simple poles, which we have already discussed in the previous two cases. So we will focus only on the first term. In such cases, first we have to rearrange the denominator in the form a square plus b square. Here a is s plus alpha and b is beta. And after converting the denominator, we will convert the numerator in terms of s plus alpha and beta. After rearranging the expression of numerator and denominator, we will put these values in the Laplace transform function like this. And from the help of previous lecture, we can find the time domain signal corresponding to the Laplace transform Fs. These are the three common cases by using which we can find inverse Laplace transform of common signals. But observing carefully, we can see there is a limitation in the degree of denominator and numerator. So what if a question like this comes where the degree of numerator is greater than degree of denominator? In such case, if you apply directly the Heaviside residue theorem, then obviously your answer will come wrong. In such cases, first you have to divide the numerator with denominator by using long division method and represent this expression in terms of quotient, which is Qs, and remainder Rs divided by denominator ds, which will come out s plus 1 plus 4 divided by s plus 3. In the later expression, you can apply Heaviside residue theorem separately. Now the question comes, what we are supposed to do with the other two terms? Both these terms can be very easily converted into time domain. As we know, one is the unilateral Laplace transform of Dirac delta function, and as a general property of Dirac delta function, we have unilateral Laplace transform of derivative of Dirac delta function equal to s. This is a general property of Dirac delta function which you can also derive yourself. In the previous lecture, we have discussed various properties, and the second property was of differentiation in time domain. By using that, you can verify this general property of Dirac delta function. So you see, it is quite easy to find inverse Laplace transform even if the degree of numerator is greater than the degree of denominator. The only calculations you are supposed to do is in Heaviside residue theorem. Otherwise, the quotient, if it is present, then it can be solved very easily. Now we will see another point which might be a little bit confusing. Suppose that we have two signals, exponential minus at multiplied by unit step signal and simply exponential minus at. The unilateral Laplace transform of both these signals will be the same, which is 1 upon s plus a. However, if we find the inverse unilateral Laplace transform of 1 divided by s plus a, then the answer will be only exponential minus at multiplied by unit step signal. This is because if you see the unilateral Laplace transform operator, then you can clearly say that it integrates the time signal from t is equal to 0 onwards. It simply ignores all the values before time is equal to 0. And since the operator has itself nullified all the values before t is equal to 0, there is no way we can determine the behavior of the signal before time t is equal to 0 by using the inverse unilateral Laplace transform. Also in the shown diagram, we can see even though the shown two signals are not same, but their values differ only for the region when t is smaller than 0. Otherwise, they are exactly the same when t is equal to or greater than 0. That is the reason the Laplace transform of both the signals came to be exactly the same. So, try to remember this point. You have to simply multiply unit step signal as it automatically cancels all the negative time values. Another example we can see from the previous lecture, we know the unilateral Laplace transform of sin omega t is omega divided by s square plus omega square, and the unilateral Laplace transform of sin omega t multiplied by unit step signal is also the same. But the inverse of omega divided by s square plus omega square is only sin omega t multiplied by unit step signal. As a matter of fact, the standard test signals in control systems usually start with time t is equal to 0, like ramp signal, unit step signal, and parabolic signal. However, in the subject signals and systems, there are sinc and sampling functions which have values at negative time also. But we are not concerned about these signals in control system. Here we are done with the topics of other subjects which will be required in understanding our main subject control system. But it does not mean I have taught you each and everything about the topics we have discussed till now. For example, there are few more properties of unital Laplace transform which we have not seen in the previous lecture, like time shifting, time scaling, and convolution. Also, there are proper derivations of each and every property which we have seen in the previous lecture, but we have not covered them. We have simply seen the final results. I am not here to show you how much knowledge I have. I am here to teach you what you must know regarding control systems if you are an undergraduate student, and I have also discussed the topics from other subjects which, if you know properly, will make it easier for you to understand the topics of control systems. I hope you have enjoyed the lecture.